So here they say we are given this geometric series 3, 6, 12, and it goes on to infinity actually. But here they say it goes on to a certain number of terms, which we don't really know. That's fine. Now, firstly, they say we need to write down the general term of this series. And after that, we need to calculate the value of k such that the sum from p equals 1 to p equals k of 3 over 2 times 2, which is further raised to the p, is equal to this value. Okay, well, the first question says we need to write down the general term, so we don't really need to calculate it now. And writing down the general term of a geometric series is actually the easiest thing in business because you know that it's a times r to the n minus 1. You just need to be worried about finding a as well as your r. So our a here is going to be 3, and our constant ratio, 6 divided by 3, that gives us a 2. 12 divided by 6, that is a 2 as well. And you just raise this to the n minus 1. So that's all you needed to do for the first term. But now it's time for us to calculate the value of k such that this series will be having this sum. And I really want you to realize that they played a trick on you because it's the same series really. They just wanted to trick you to see if we can manipulate your expressions. And this is what they said. We have the sum from p equals 1 to p equals k, but it's the sum of 3 over 2 times 2, and this is raised to the power what? P. Okay, right. Well, first and foremost, I actually want you to realize that what? 3 over 2 times the 2 there, which is further raised to the p. This is how you can rewrite this. 3 over 2 is the same as 3 times a half, which in turn is the same as 2 to the negative 1. So now you further multiply this by that. And of course, when multiplying powers of the same basis, you simply add the exponents. This is exactly the same as the general term that we have written before, which we said it's 3 into 2 to the n minus 1. It's exactly the same thing, just that they played a trick on you. So yes, please make sure you can see things like that. Okay, fine. So now we know that this is actually 3 times 2 to the p minus 1. And here they said the sum of this is 98,301. All right. We need to find the value of p. No, the value of k, I'm lying to you. So the question is, what is k? Well, k is actually the number of terms. Because in order for you to find the number of terms, you say top value minus the bottom value plus 1. So you find that there are k terms in this series. Okay? But now you know that it is a geometric series, so we need to know what is the first term as well. We don't need to expand it in order to get the first 3 terms. But we can actually expand it in order to get the first 3 terms. That step usually has a mark in the exam. So let's just do that. So, well, we now know that this is actually the same as 3 times 2 to the p minus 1, right? But now we know that we begin substituting from p equals 1. So we have 1 minus 1 there. And then we have 2 minus 1. And we have 3 minus 1. And this goes on up until the last term, which we obtain by substituting p equals k. So we have k minus 1. And I just want to emphasize that even if you did it like that and just said 3 over 2 into 2, 1. 3 over 2 into 2, 2, and so forth, it's still perfectly fine. Yes. So what I'm saying is, even if you didn't realize that this pattern is actually like that, it's not a problem in this case. Okay, fine. So 1 minus 1, that gives us a 0. 2 to the power 0, that is 1. So the first term is going to be 3. Well, it's actually the same series as before. Well, this one will be 6 and this one will be 12. And this goes on up until the last term, which will just be 3 into 2 to the k minus 1. Then you can tell them that the first term is going to be 3 and the constant ratio is going to be 2. And you know that the sum of the first number of terms for a geometric series is given by a into r to the n minus 1. And this is divided by r minus 1. You could have said 1 minus r to the n, 1 minus r. Well, both of them are equally correct. Then now you come and say, well, the sum is given to us as 98,301. Well, the first term, that is 3. The constant ratio is 2. The number of terms, that is k. And this is divided by 2 minus 1, which is just 1. But let's just write it for now. So then 2 minus 1, that gives us a 1. So we actually have this thing. So now we divide both sides by 3. We say 98,301 divided by 3. Then we get 32,767. And we take the 1 to the other side, so it becomes positive. So we have 2 to the k, which is equal to 32,768. I'm just trying to minimize the number of steps here. And let's see if we can write this value in exponential form to base 2. Well, as a matter of fact, we can. It's simply going to be 2 to the 15. So the bases are the same. We simply equate the exponents. So we find that k will just be 15. Yes, that's one way in which they could have asked it, or they could have said to you, calculate the number of terms in this series.
A geometric sequence and arithmetic sequence have the same first term. The common ratio of the geometric sequence is 1/3. The common difference of the arithmetic sequence is 3. The sum of 22 terms of the arithmetic sequence is 734, more than the sum to the infinity. More than the sum, is 734 more than the sum to infinity of the geometric sequence. Calculate the value of the first term.
Right, thank you, sir. So a geometric sequence and an arithmetic sequence both have the same first term. Okay? The common ratio or the constant ratio of the geometric sequence is a third. Okay? The common difference or the constant difference of the arithmetic sequence is 3. Okay? The sum of 22 terms of the arithmetic sequence is 734 more than the sum to infinity of the geometric sequence. What does this mean? It means the sum of these 22 terms in an arithmetic sequence is actually 734 more than the sum to infinity, which means if you take the sum to infinity and you add 734, then you get the sum of the 22 terms in the arithmetic sequence. More than you add, less than you subtract. So knowing what we know, we need to calculate the value of the first term. And we know that it's possible to find the sum to infinity of this geometric sequence because the constant ratio is less than 1, but greater than -1. It's 0.333, which is recurring. So it's not a problem. Well, let's go ahead and show with flames. Well, first things first, we need to focus on the arithmetic series. So we tell them that A is going to be 3. That's true. The constant difference, they told us that it's going to be a third. And here you don't really need to specify that it's for arithmetic, for geometric, because the equations are different. The formulae, that is to say. So let's begin by doing what? By calculating the sum of the 22 terms of an arithmetic sequence. So we say, well, the sum of 22 terms is equal to 22. Remember, it's always nice if you write a formula, but it's not compulsory. There is no mark for a formula. So you have 2 into A. Why did I say A is 5? I'm not sure why I said that. But A is A. A is the first term. So maybe I can say T1 equals A. I'm sorry for saying it's 5. I don't know where it comes from. Then here we have our 2A. And we have n minus 1 times D. Well, it's the sum of 22 terms. So we simply have 21 here. Or you can formally say 22 minus 1. And you times this with the constant difference, which is 3. I think they said it's 3. I'm messing things around here. Sorry once again. The constant difference is supposed to be 3. Right. And now we can close this one off. And when we simplify this, well, 22 divided by 2, that's 11. And here we have 21. 21 times 3, it's 63. So here we have 2a plus 63. And if we simplify this even further, well, we find that 11 times 2, that's 22a. 11 times 63, that's 693, all right? Now it's time to find the sum to infinity. In order to find the sum to infinity, we only need the first term as well as the constant ratio. Well, the first term is given to us as a. We don't know what is the first term, but we know that it's the same for both of these sequences. And the constant ratio is actually given to us as a third. So when we say 1 minus 3, we actually get 2 over 3. And since we know that division has never divided another division, we just take a and we multiply it with the reciprocal of this. So we simply get 3 over 2a. That is the sum to infinity. Well, we go to the most important part now. They told us that the sum of the 22 terms in an arithmetic sequence is actually equal to the sum to infinity plus 7 therefore. Yes? So then what does it mean? It means 22a plus 693 is actually equal to 3 over 2a plus 734. That's what it actually means. And collecting the like terms, of course, we take this one to the other side, and similarly, this one to the other side as well. And when you say 22 minus 1.5, well, you simply get 20.5, 41 over 2a. And when we say 734 minus 693, you get 41. And when you multiply both sides by the reciprocal of 41 over 2, which is 2 over 41, we find that a is going to be 2. Then we can now conclude and say, therefore, the first term will simply be a beautiful 2 there. So yes.